Hello everyone! Welcome to another new chapter in the Fuzzing Book. Today we're going to explore how to generate the most complex inputs on Earth, namely by testing compilers. Compilers take programming code as inputs, and programming code is probably the most semantically rich input that exists on Earth. So why not see whether our techniques work for an input that is as complex as that? Ladies and gentlemen, welcome to testing compilers. Testing compilers, here we go. So, with everything that we learned so far, notably in our chapters on grammars and grammar-based testing, all we need in order to test a compiler, apart from checking whether the compiler does the right thing and whatnot, first and foremost, we need a device that generates inputs. And so, how about writing a grammar for a programming language? A grammar that we can use to produce inputs for this very programming language, and which we can then use to feed into the compiler. So, why not? Let's do this right away. But before we do that, well, there's going to be a little problem. And the problem is as follows. So let me first get a few inputs here in order to get the compiler running. Here we go. We have a grammar now, so that's fine. And the problem I want to illustrate comes from a very simple problem. So you remember we had a grammar for expressing arithmetic expressions. Arithmetic expressions are typically parts of programming languages. And if we have that grammar, then we can also go and generate inputs from it. For instance, using our ISLA infrastructure, we can go and create a solver that takes this very grammar and then produces outputs from it. Here we go. This looks like a grammar to me. This looks like a valid arithmetic expression to me. This also does. And here, sorry, what's that again? Here we go. And all these things actually look good. So for producing, that's not too much of a problem. However, and here comes the problem, not only do we want to produce correct inputs, but we also want to parse and mutate inputs in programming languages. For instance, because we already do have tons of existing code available, and we want to mutate this. And now that's where the problem comes along. If we parse inputs that exactly adhere to our grammar, like this one, all of this works well. But as soon as there is a single extra space in here, something like that, you see, 2 spaces in here, what happens is we get parsing errors. Likewise, if we do have no spaces in here, then we get also a parsing error. And if we have something like comments in here, we get a parsing error. So what we could do is to extend our grammar such that, for instance, comments or white spaces would be allowed at all places. But the thing is, comments are allowed everywhere. I mean, anything, everywhere in a program I can have a comment, and therefore I would have to adjust my grammar accordingly such that, well, pretty much at any point in this grammar, within a factor, within an expression, whatsoever, at all points I can have white spaces, I can have comments, and that's lots of problems. And the thing is that a compiler by itself also does not work that way. Compilers typically consist of a part that does the lexical analysis. This is called the lexer or the scanner, and this takes care of white spaces, it takes care of comments by ignoring them, and it actually decomposes the input into a series of tokens, and it is these tokens that then make up the grammar. So there would be a token for the individual characters, like opening parentheses, closing parentheses, or for individual digits, or even for actual integers. meaning that when the compiler sees the input, all of these comments, white spaces and whatever already have been moved away. And this means that when we are composing the grammar for a compiler, we don't need to care about anything. We don't need to care about this at all. Well, unfortunately, this does not help us with our current problem, because if we want to define a complex input language, say for a programming language, well, in our infrastructure, we do not have a separation between the we do not have a separation between the scanner and the parser. The scanner that composes things in token gets rid of comments and everything. No, but we only have one grammar, and this would make our whole input processing very complex. And this is where a particular rule of thumb comes in. If you do have an existing parser for a language, it's a good idea to make use of it, because such existing parsers already take care of all the specific features of the input language in question, such as getting rid of comments, handling white spaces and whatnot. If you look at real-world scanners for real-world languages like C++, you'll be amazed at how many exceptions there are. So it's always a good idea to rely on existing infrastructure as much as possible. So what we want to do is we wanted to write a fuzzer for Python. And we do this because everything so far has been in Python and we don't want to extend things any further. So we can simply stay in Python. Also, fun thing, it is actually easy to access the compiler, or more precisely, the parsing infrastructure of the Python interpreter in Python. Python provides an extra module for this very purpose. And I'm going to illustrate this using a simple example. So let's come up with this very simple example here. I have a little program that prints out hello world. We can go and invoke this thing, blah, hello world, here we go. Arguably one of the simplest Python functions you can think of. And what we can now do is, all using a material that is on board of Python, we can go and grab the source of this very program, so we can actually make use of the inspect module to get the source code of this very function. The beautiful things you can do in Python. And we can also print that out, and you're going to see that main source is a string that actually holds the source of the original code. So what do we do with this now? The idea is to actually make use of the Python parser to convert this into an expression in which all the lexical scanning, all the comments, all the white space already has been processed. And the result of this phase is called an AST, or abstract syntax tree. There's a module in Python for that. It's actually, there's the sentence, there's an app for that. In Python, it's more like there's a module for that. And the module for abstract syntax trees is called, not very surprising, AST, for abstract syntax trees. The AST model provides a method named parse. It's called AST.parse. And AST.parse takes the source of, we actually see this here. How cute is that? Parse source into an AST node, or more precisely into a tree, abstract syntax tree. So we can parse in here a Python function or a Python code like x equals 3, or we can also put in here the main source that we originally had. And then what we get is, we get an abstract thing here, which is called an AST.module. That's not super helpful because, we don't see this thing. But what we also do have is a mechanism for visualizing this abstract syntax tree. And this is precisely what we're going to do. So we have a function called show AST. And if I do apply this to show AST, what we're going to see is the abstract representation of our program. And this abstract syntax tree, this abstract representation looks as follows. At the beginning, we have a node called function dev for function definition. And it has 3 children. It has a name called main. Main, here we have it. It has arguments. Arguments. Well, this has no arguments, so nothing happening in here. And the main part of main, the function body, is an expression which has a call. And this call is a call to a name which is called print. And this call has an argument, namely a constant, named hello world. So this is what this AST looks like. Okay. We can also go and print this out in textual form. Then you're going to realize that it becomes much more complex. This is what it looks like when we print it out, and these are things that are actually removed from the tree representation. So what you see here is that this AST structure is in fact a module with a body that is a list which starts with a function definition whose name is main and where the arguments are all empty, and where the body is an expression, and the expression is a call of a function with a particular name whose name is print, and with arguments that start with a constant whose value is hello world, and no further arguments in here, no keywords, no decorators, no type ignores. All of these calls in here, such as module, function def, or expression, or call, which come in uppercase characters, actually are objects of the AST module. So we can actually go and say, okay, we can actually go and say, I wanted to create a module, so I can say AST module, there we go. And now I can put in the arguments that would be in here. And this would allow me to create this very abstract syntax tree that we have over here. Most importantly though, I can also go, and here comes the fun part, I can also go and unparse the whole thing. So if I do have a tree like this, main tree again, I can go and unparse it. So I can say ast.unparse, and then my AST will be converted back into a string, which we get here. Definition of main print hello world. Well, let's give it a print such that we actually see the whole thing. So we have a means to convert a piece of Python code with all bells and whistles, such as comments and whatnot. We can convert this into such a tree which actually has plenty of features in here. So abstract syntax trees are, well, among the most complex and most convoluted data structures in the world. But the neat thing is we can also convert these trees back into actual code. Notice the difference between the original code and this one. I'll give you 3 seconds. This is what comes out after converting the tree back into code. And something else that we have up here, this was our original code. Yes, there are 2 differences. First difference is the comment is gone. Why is the comment gone? Because when converting this original main source into a tree, well, the comment was eliminated by the scanning phase. Only those parts that are relevant for the code remain, and comments, at least from a computer's perspective, are not relevant. Second, you'll also notice that the quotes are different. Originally we had double quotes, and now when we unparse things we have a single quote. Well, that's simply because in the abstract representation that we have over here, the information about which quotes these were is actually gone, and the unparser simply prints out the string using some canonical form. So, how do we make use of this if we want to test the compiler? The idea is very simple. Rather than testing the compiler with concrete input, such as this one, we go and instead make use of the abstract syntax tree, namely this one, to create abstract syntax trees that are valid. We create one abstract syntax tree after another, and we create a grammar that produces all these abstract syntax trees, one after the other, with all the correct arguments. And these abstract syntax trees can then be converted into actual Python code, which we can feed into the Python compiler. Actually, we could also take the trees themselves. So just to show you that this actually works, I can go and simply import all names from the AST module. This is an n-type pattern, but this allows me to take this very expression here and to directly convert this into a tree. So I can now go and say tree equals, well, module and all that. Here we go. Let's see if this works. Oh, it works. Oh, I'm always excited about that. And this tree, well, we first need to make a very small fix to it, because trees in Python actually require that there be locations. So there's an extra module, an extra function in the AST module that is called fix missing locations. If you don't do that, you're going to get plenty of errors. But once you've done that, then you can go and say print AST unparse.tree. Here we go. And then, well, you get again hello world. And we can now go and say I'm going to change this tree expression somewhere. So I'll be saying good. Oh no, why not? Come on, hallo Welt. Well, that would be German, so substantive. Here we go, and then the whole thing then produces code that is hallo Welt. Or we can also change the function name here. Or, well, let me see if this works. Maybe, just maybe, sorry, no, that was wrong here. But maybe, just maybe, we can also add another argument to the whole thing. I haven't tried that before. Does that work? If I put in another constant in here, in this list of arguments, and I print this out. Oh wow, this works. And now we have added another argument to our printing function. Okay, so now we have another argument whose value is 42, and of course we can also change the value of the print function, whatever, name it pprint for pretty printer, and then we have a name of pprint in here. And you see that by altering these individual parts of the abstract syntax tree, we can generate more and more code. And the idea now is to have a grammar that gives us all these individual elements, function def, call, name, and so on. And we create a grammar for this that will give us an AST. We evaluate this whole thing, then we evaluate these big expressions. We get an AST from that, and this AST is then something which we can feed into AST.unparse, and then we get the concrete code as a string. This is going to make our life much easier, simply because we will always get something that is valid as long as we adhere to the rules of the abstract syntax tree. And this also allows us to parse existing code into an abstract syntax tree, to mutate it, and then to print it out again, and even do gray box fuzzing of compilers, all these things that we have seen before, all the things that we can do with grammars. So rather than taking concrete code, we use the AST as an intermediate representation. What do we get out of this? So the whole thing still is pretty complex. It's a huge effort to actually specify all these individual rules. I'll give you a simple example right out of the notebook that in which I have defined all these individual grammars. It's it definitely was some work to get this done. So let's see, where do we have it? One more second. Here we go. So for simple constants, for instance, okay, constants, what we see here is we start with strings that contain any character except for double quotes and backslashes, for reasons that we're going to see soon. And now we create expressions in abstract syntax tree syntax. So an expression in Python consists of this, in Python ASTs consists of an AST expression object whose value is, well, an expression. An expression is either a constant or an expression. A constant, as we have seen right now with our value of 42 or our value of hello world, is written like this. And then we have literals, and literals are either strings or integers or floats or booleans. And strings, well, this is complex. It's something this is a double quote followed by a series of characters that are not double quotes and another double quote. And we can also have single quotes, which is anything followed by not a single quote. Here we go. The actual rules are more complex than that. And we also have rules for integers, for floats, and all that. We have values for booleans. You will find actually in every such grammar that there's a couple of things that are not supported yet. And this is something which we can now use to actually generate a grammar from it. Here we see the abstract syntax, expression, an expression whose value is a constant, whose value is false, and this translates into concrete code, false. A constant whose value is 2, here we go, this is 2. A constant whose value is none, this is none. And we can of course make use of all our fun grammar testing in order to get grammar coverage. We could also go and assign probabilities to all these parts. This is grammar testing as its finest. And of course our grammar can also parse such ASTs. So here's some constant code, 4711. We go and we parse the whole thing, then we access the expression node, then we dump it all out, and here we have the whole thing again. And this is then again, this string is something that we can parse and that we can check. And here we go. This is actually parsable. So the whole chapter from here on mostly essentially consists of all the individual rules for the abstract syntax trees of Python. Here is a list of all the individual parts of that grammar: assertions, assignments, attributions, augmented assignments, things like plus equals, multiply equals, binary options, break, call, compare, delete, dict, pass, set, slice, and so on. And plenty of individual arguments too. So this is a really complex grammar where you can actually check how this is done in the real world. If you want to test a compiler, that's actual real world. You can find out all the individual rules in there by actually checking out the grammar itself. Most importantly, though, we do have the culmination of all this, a fuzzer that actually produces Python code. So I'm going to make a big jump here, how all of this works. So we have a Python fuzzer module, and we can import the Python fuzzer. Here we go. Haha, oops, no, sorry, what did I do? Here we go, sorry, no, SKY, here we go. So I have the Python fuzzer, and I can now go and create a Python fuzzer. That's very simple. Python fuzzer from that very thing. And the Python fuzzer, you're not going to believe this, again, has a method to produce Python code. By default, it actually produces function definitions. So here we have a function called d, that is pass. We have a function called f. We have a function called y. We have all kinds of individual functions in here. And these, oops, what happens there? Oh, no, sorry. We need to create a new one. Here we go. So we can have one function after another, which is fun. And as an argument, you can also pass an individual language element, and then you can, oh no, what did I do wrong in here? Oh no, that's not how it works. I'm so sorry. The Python fuzzer takes an argument. You can also ask the fuzzer to start with a particular element of the language, and there's a long list of elements. We'll come to that in a moment. And this allows you, for instance, to create inputs that consist of a while loop. The code that you see in here, what is that? While set, and this is a slice actually, with an empty, all these things are very weird. And this is what you get when you're producing entirely random code. The good news is all of this can be parsed. And since it can be parsed, it can also go through further steps of a compiler. What you typically cannot do is execute the whole thing, because if you execute the whole thing, in most cases, you're not going to get very much of it, but you can certainly test all the steps of an individual compiler. What are the things that you can do with that? You're going to have fun with that. So the actual grammar is in a variable called import Python AST grammar. You see there's plenty of sub-grammars in here. And the actual grammar has all of these elements: assert, assign, attribute, and so on. And if you want to see what the actual grammar looks like, haha, this is really gigantic. Here we go. And what is a Python AST? It is a module, and we have a rule for expression. An expression is a constant, or an expression, or a dictionary, or set, or tuple, or boolean, or whatnot. An expression is an expression object whose value is particular. We've seen this again. So strings, literal strings, are still in here. So that's still fairly straightforward. But further down below, well, we get what is an empty set, what is a tuple, what is a Boolean operator, what operators do we have? We have add and sub and mult and metmult. What is metmult? Need to look this up. Unary operations, comparisons, compare operations. We have identifiers with all the letters that are and numbers that are allowed in identifiers. Oh, we have attributes, we have subscripts, we have slices, we have starred elements. All of this is part of the abstract syntax of Python. It was quite a work to get all of this together and to get it work. I'm pretty proud that I was able to do this. This took me, if I recall it right, something around 3 days to put it all together and to make sure that it actually worked. This was built from the official AST documentation. And yes, this Python fuzzer is able to produce all of these individual elements. And with this, you can actually go and create plenty of Python inputs. The downside is that I have not managed to crash the Python interpreter with any of the code that comes out. Python is a very, very robust infrastructure. But the chapter also contains information or ideas on how to make use of this for mutation-based testing, that is reading in code, parsing it into an AST, mutating the AST, unparsing it again, and then feeding this into a compiler. There's also examples on how to make use of this for gray box fuzzing and other stuff. So, if you have a compiler for language of your choice, say C or Rust or Go or JavaScript whatsoever, either you do have a parser and an unparser available, then by all means make use of it, and then you can follow the steps as shown in this chapter, or you'll have to write your own parser and your own unparser. Yeah, and then your life will become pretty miserable for a couple of weeks until you actually have a parser available that is able to parse real-world C code. Or you just dig deep into your pockets and you buy one. Real-world systems that actually go and analyze C code, parse it, mutate it, write it out again, make use of commercial parsers. These are somewhere in the 4 to 5 digits of, well, euros, dollars, you name your currency. Yep, and these are all expensive and hard to get. Well, fortunate for us, how fortunate for us that we are all doing all of this within Python, such that we can make use of the Python language altogether. I encourage you to go through the code to explore how the interaction between input code and ASTs, parsing, unparsing, all of this works, and how we make use of this to create this very big grammar. I think this is one of the most complex grammars in the entire Fuzzing book. Also have fun with the exercises that we provide. I wish you a great day and enjoy fuzzing compilers. With that, thank you very much and enjoy the code.